Okay, let's look at question 3 on the higher combined paper. So we've got an electric wheelchair here. The wheelchair moves at a constant speed of 2.4 meters per 4.5 seconds. So whenever we see a question that is going to involve a calculation, we should highlight our numbers and units and then use those numbers and units to work out what we've got. So we have got here 2.5 meters per second, so that's going to be a speed. It could be a velocity. Remember, velocity is just speed but with a direction. And we've got 4.5 seconds, so that is going to be a time. We should also be noting that meters per second is the correct unit for speed, so no calculation there, and seconds is the correct unit for time, or the standard unit for time. If it was in minutes or in hours, we would have to convert it to seconds. It wants us to calculate the distance, so I like to put a box around what I'm trying to find, moved by the wheelchair. And we're actually given the equation. So you might not be, this same question could be given and you could have to find the equation using the data sheet that you're going to get on the day, and therefore it would be worth an extra mark, so it would be worth 3 marks. But because we're given the equation, we just have to input our numbers. So I always like to use FIFA as an acronym to help me remember what to do. So I'm given the formula. Next, I'm going to input the data. The F would be to fine tune it if I need to, if I need to do any conversions or if I need to rearrange it. And the A is obviously to write down the answer. So distance, I know distance, so I'm just going to leave it as distance. I should say I don't know distance, sorry. Equals speed times time. So the speed is 2.4 meters per second, and it's the correct unit, so I'll just leave it as 2.4, multiplied by the time, which is 4.5. Okay, we've got to get that calculator out. Even if it's an answer you think you could do in your head, no, don't. So we've got 2.4 times by 4.5 gives us 10.8. All right, times 4.5. Notice I'm doing it twice just to check I get the same answer both times. I did. I got 10.8, so let's put that away. So equals 10.8. Make sure that you are really, really clear that that is a decimal place. All right, sometimes you see this in exams. People just put the dot with the biro and it doesn't show up very clearly. And in the end, it looks like 108 and you're going to lose marks for that. New thing about AQA, which hasn't been the case on mark schemes in the past, but apparently is the case now, is that you must show your working out. So even if you get the answer correct, if you don't include any working out, you will not be credited with all the marks. So you must include your working out. What could be a reason for the speed of the wheelchair decreasing? Okay, so we're going to go through these values and these lists and see what would make that wheelchair slow down. So it going downhill. Well, let's think about it. If you've got an object like this and it's going downhill, well, actually that's going to speed up, isn't it? Yeah, I always like to think about if you're on a bike. If you're on a bike and you go downhill, you're going to get faster. So nope, it's not going to be that one. Going uphill. Okay, here's our object going uphill. Well, yeah, that's going to be harder. So yeah, that's valid. Its store of kinetic energy increased. Well, for the amount of movement energy it has gets more. No, if it's slowing down, that wouldn't be the case. So we get rid of that one. It used more power from its battery. Well, it's an electric motor, so the more power, the more energy it transfers every second. If it's transferring more energy, the more it's going to go faster. So again, it would speed up. So it can't be that one. So the only one that makes sense is the fact that it's going uphill. A student measured how the distance travelled by a wheelchair changed over time. Figure 2 shows a sketch graph of the results. Okay, so this is in here because we know that one of the areas of focus is going to be on speed and the forces involved with speed, and including that is distance time graphs and velocity time graphs. So this is a good chance just to have a look at these and see what these mean, because obviously it won't be this exact question, but it'll be a question something like this. So first off, we should see any flat areas on a distance time graph is stationary. That means that the object is not moving. On a velocity time graph, a flat line doesn't mean stationary. A flat line means constant speed. So it's really common for students to get these two mixed up. All the other lines, A, B, and D, the lines are going up. So that's showing an increasing speed. sorry, it's showing an average speed that is actually moving. So it's showing a constant speed. An increase in speed would be acceleration, and that would have a curved line like that. So if we have a look at this, the steeper the line, so think about again, you're on your bike. If you were sat at your bike and you're here and you were trying to go up that hill, that's not that steep. Whereas if you're trying to go up that hill, that's very steep. So D is a much steeper line than A. The steeper the line, the faster the object is going. So in which section of the graph A, B, C, or D did the wheelchair travel the fastest? Give a reason for your answer. Well, the steepest line is D. We can see that because if I just draw a line here, okay. Now what I'm going to do, you won't be able to do this with yours, but you can do the same thing that I'm about to do with a ruler, just to check steepness. So if I move D, so I can move my ruler, you can see that actually it's a lot steeper than B. So if we start at the same place, if you had your bike, the line you would want to go up is B, because that would be easier. D, really steep hill, and it's a lot steeper than A. So D is the steepest gradient, therefore it is going to be the fastest speed. So it's going to be D. Reason why is because the gradient of the line is the steepest. The gradient of the line, just while I run it, can be used to figure out the speed that an object's going. It can't on this one because it's a sketch graph, but what you can do is you can draw yourself a triangle on the line. I'll show you how I did that rather than just using this. So basically you would draw a line at the bottom and you would draw a line at the top like that, and that creates this triangle here. And then this area is your y and this area is your x. And what you do is you do the change in y divided by the change in x. So you just read some numbers off the graph. So you'd read whatever this number said here, and you'd read whatever this number said here, and you'd look at the difference. So that's your change in y, and you do the same here and here, and you look at the difference. That's your change in x, and that will give you your speed. But we don't need to do that for this one, so I'm just going to get rid of all that. The student used a data logger with a distance sensor to record the data. Give 2 advantages of using a data logger rather than a stop clock and a tape measure. So we can think about this experiment you might have done is the one where you've got a trolley in a car and you put the trolley on a ramp like this. So here's your ramp, and you put your trolley down your ramp and your car travels down, and you can look at how the height of the ramp affects the acceleration of the trolley. That's a required practical. Now, when you're doing it, you can do this with a stopwatch. You can get someone to hold the trolley at the start. You let the trolley go a certain distance, maybe a meter, I don't know. And then what you do is you time how long that takes, and then you can use that to figure out the acceleration by using a formula from the data sheet. The way to do that more accurate, though, is to use what we call a data logger. And a data logger is you've got something at position A and you've got something at position B. These are called light gates. And what happens is when an object goes through the light gate A, we'll represent with this beam, it opens a beam and it breaks that beam, so it tells the computer start recording the time. And when it goes through B, it breaks that beam again and it tells the computer stop recording the time. So you get a very, very accurate timing. It's used in the Olympics. If someone's running the 100 meters and you see, Usain Bolt's got a new world record of 10.58 seconds for his 100 meters. Sorry, 9.58 seconds. There wasn't a guy stood there with a stopwatch doing that because that's not going to be accurate. So we use this thing called light gates, which is connected to a data logger, and it just gives us a really accurate time. So 2 advantages of using this data logger, it's going to be a more accurate measurement of time. And the other thing as well is sometimes, when you've got a stopwatch, I know when I set this up in my classroom, the first thing I always get people to do is just make sure they know how to use the stopwatch. Because what tends to happen is we tend to do the experiment, set it all up, and do it, and I go, okay, right. So what do we get? And they went. The student often says, oh, I forgot to press the timer, or I pressed the wrong button on the stopwatch. So a data logger, that can't happen. So it means that it reduces the human error, we call it, which is a type of random error. So that it reduces human error. Okay, next question. The velocity of the wheelchair changes as it accelerates to its top speed. Figure 3 shows a sketch graph of the changes. Again, there's no numbers on this y-axis or x-axis, so it's just a sketch. We're not going to have to figure out any data from it. But this is a velocity time graph, and as I said with the data time graphs, people get confused between them. So this time we have got this area here where we've got an increasing gradient, and an increasing gradient on a velocity time graph, that is acceleration. So you can see that the object accelerates quite quickly, and then we've got this other gradient here where it starts to slow down. It's still accelerating, and then we've got another part at E where it's flat, so the object won't be accelerating, will have a constant speed. So we've got 3 stages in this graph at least. So we've got initially the object accelerates quickly, then it starts to slow down, and then it's not slow down, but it starts to speed up less with less acceleration. So its acceleration reduces. So we've got very fast acceleration, less acceleration, and then coming at E to a point where there's no acceleration. We've got constant speed. So when the forward force of the wheelchair is constant, it accelerates on flat ground. So let's draw that out. So here's let's say this is the wheelchair, and we've got a forward force like this. So let's give it a number. It's a random number. Let's say it's 100 newtons. So if the forward force is bigger than the backward force, we're going to get acceleration. In this case, we've got 100 newtons forward. There's always going to be some resistance in the opposite direction. So let's say that there was 50 newtons in the opposite direction. So we've got an overall resultant force here of 100 minus 50 equals 50 newtons in that direction. So that's why that's a very bad error. Let's try that again. So that is why we get the acceleration in that direction, forwards. So what are these backward forces then? What forces is this 50 newtons? Well, it could come from friction, the wheels rubbing against the surface, or it could come from air resistance because the wheelchair is traveling through the air, so it's going to be colliding with air particles, causing some resistance there. Let's see what options we've got and which ones make sense. So first one we've got is air resistance. So we've already said that that's probably going to be the reason. Magnetism, nope. Tension, nope. Weight, nope. It's going to be air resistance. So air resistance is going to reduce the acceleration. The more air resistance, the slower the acceleration, because the bigger this backward force is going to be. The less air resistance, the faster the acceleration, because the forward force is there's going to be less backwards force, so the resultant force is going to be bigger. So you could streamline your wheelchair, make it go faster. Explain the acceleration of the wheelchair at point E. All right, point E. So let's go to point E. This is point E, and we've got this flat line, so it's a constant speed. So if we've got a constant speed, we've got no acceleration. So we can say there is no at point E as the wheelchair is traveling at a constant speed. Okay, so we've described it, but we have actually been asked to explain it. So explain means say why. So why is there no acceleration? We can go back to this diagram here. In this diagram, there was acceleration because the forward force was bigger than the backwards force. So let's take off all of this. And in order to get no acceleration or a constant speed, the forwards force and the backwards force must be the same. And if that is the case, what you do is you have 100 newtons minus 100 newtons, which gives you 0 newtons. So we can say there is an overall resultant force of 0 newtons, therefore we travel at a constant speed, or there is no acceleration. So that explains what we're seeing at E. So no acceleration at point E, as the wheelchair is traveling at a constant speed. This is because the forwards and backwards forces are equal. Sometimes we would say balanced. Both would be correct. This is because the forwards and backwards forces are equal. So the overall resultant force is 0 newtons. And if you have 0 newtons of force, then you can have constant speed. So the car will either stay going at the same speed if it was already moving, or if it was stationary to start with, it won't move at all. The wheelchair starts on rest. Okay, rest. Let me get the highlighter back out. Rest, whenever they say rest, it means 0 meters per second. And that is its initial velocity or initial speed. So its starting speed is 0. It accelerates at a constant rate until it has a speed of 1.5 meters per second. So that is going to be its final velocity. And the wheelchair travels a distance of 2 meters. So meters are the correct units for, or the standard units for distance. So that is a distance. Calculate the acceleration of the wheelchair. So that's what we're trying to find. And use the physics data sheet. So this is a bit tricky because it's over 2 pages. So what I'm going to do is I'm just going to list what I've got in the top. I have got a initial speed of 0 meters per second. I've got a final of, let me just check, final speed is 1.5. I have got a distance of 2.0 meters. All of these are looking to be to 1 decimal place. So our answer should be given 1 decimal place too. And it wants me to find an acceleration, which I currently don't know, but it will be in meters per second squared. So I need to find a formula that has initial speed, final speed, distance, and acceleration. So I'm going to go to my data sheet. This data sheet is the triple one, but it doesn't matter. It contains the same equations. The triple one just has a couple of extras on. It hasn't got any of them missing. So we are looking and going back to our paper and constantly having the two side by side. So it's a bit easier for you than it is for me. Because you can have them, as I say, like looking at them at the same time, whereas I'm going to have to jump back and forwards. So I want something that's going to have an acceleration in there, definitely, and then it could have initial speed, final speed, and distance. So I'm looking for acceleration, the word acceleration, as I scroll through. Acceleration, acceleration. I've not seen it yet. So we go to the next page. So this will be the back. Remember, data sheets have a back. A lot of people forget that. Acceleration, acceleration. Still not seeing it. Still not seeing it. I've seen an acceleration. All right. So we've got acceleration here, and we've got a change in velocity, and we've got a time taken. I don't have a time here. I do have a change in velocity. It's gone from 0 to 1.5. So I have a change in velocity, but I don't have a time. So that's probably not the formula for me. Let's keep looking. Acceleration again here. We've got a distance. Yep, we've got that. And we've got, so it's this one here. Okay, so let me just take that one away. So we've got final velocity squared minus initial velocity squared equals 2 times acceleration times by distance. Okay, this is a bit of a tricky one, that one. in that there's just a lot of stuff in it. So v being final velocity, so v squared minus u squared equals 2as. So whenever we get a formula, let's use FIFA. So the formula is v squared minus u squared equals 2 times by a times by s. Now you could have written that out in words if you wanted to. Remember, we can just keep looking at that sheet and working out what they are. So the v squared is the final velocity. So let's have a look. So we're going to do the I of FIFA, so we're going to input our values. So what is the final velocity? Well, the final velocity is this one here, 1.5. 1.5 meters per second minus our initial velocity, which was 0. Remembering to square this as well. So 1.5 squared minus 0 squared equals 2. So 2 is just 2. Times by my acceleration, which I don't know, so I'll leave that as a. Times by, now people always think S is, they always get that wrong, what S is. The S is the displacement. So, wrong sheet. So we're looking at the distance on its displacement. So what was the distance? It was 2.0 meters. So we would get a mark as soon as we put that in, because that's our substitution. I'm going to use the F of FIFA now to start to fine tune this a little bit. The first thing I'm going to do before I start to rearrange it, because what I need to do is I need to make that A the subject. But before I start to rearrange it, I'm just going to do what I can do already. So 1.5 squared, I can do that already if I grab my calculator. So, because what happens is people always forget to square. So let's just get that out of the way. So 2.25 minus 0 squared. Well, 0 squared is 0, but just to make sure. So actually, we can just get rid of that whole thing. We don't even need that there. We'll leave it for now. So 2.25 minus 0 equals 2 times by a times by 2.0. So 2 times by a times by 2.0. We can do the 2 times 2. So let's do the 2 times 2. 2 times 2 is 4. So 2 times 2.0. Just remember, I said I'm going to do everything. So we end up with 4 times a. There are a couple of different ways of doing this, but I like to do this where I just do everything. So we end up with 4.0 times by a. And we can fine tune this a bit more because we don't need that 0 in there. So 2.25 is equal to 4.0 times by a. We want to make a the subject. So what we're going to do is we're going to do the inverse as to what's happening to it. So we're going to divide this side by 4.0 and we divide this side by 4.0 because whatever you do to one side of the equal sign, you've got to do it to the other. So we end up with 2.25 divided by 4.0 is equal to my acceleration. So let's do that. 2.25 over 4.0. Oh, I wrote 1.0 there. 4.0 is equal to 0.5625 is my answer, my A of my FIFA. Now, everything else was to one decimal place, so I could just write 0.6. But I'm going to put it to 2 decimal places. It doesn't tell me to give it to a number of significant figures. So I'm just going to round it here. So I'm going to say 0.56 be my answer. Be very careful on your exam paper not to do what I did by putting that 4 onto that answer box there. It might confuse the examiner a little bit. So if I was to do that, I might just circle it and just say my answer. Okay, just to make it really obvious to the examiner that your answer is that, my 0.56 meters per second. Okay, that is the end of question 3.